Hello everyone. Today I'm going to continue my discussion on counting distributions. If you remember last video or last time, I solved problems for very small values of n and k, this distribution problem. Now today, let me remind you first of the problem, okay? This is the counting distributions of n distinct items into k identical boxes. Okay? The n items are distinct, the boxes are identical. In fact, there was no condition given on whether or not a box or more could remain empty after a distribution. Okay, we were counting all of them. We counted all of them. But today, we are going to rephrase, or we are going to find a way of saying the same thing in a slightly different way with some additional condition imposed on this problem. Okay, now, but first, let's see what the possibilities of, or what the distributions of such, what the possible distributions could be for some specific values. Suppose n is 4, n k is 3. Okay? That will lead us to some kind of general. Okay, now, as I have already shown you, 4 into 3 parts could be given us as a sum of 4 plus 0 plus 0. Okay? So when you take this as a distribution, it means these 4 items, all of them are or end up in the same box, okay, all, while the remaining 2 boxes are empty because they have 0 items. Each has 0 items. Now, there are different ways of obtaining this. We have counted it last time. And the other possibility, for example, 4 equals to 3 plus 1 plus 0. And there is also 4 equals to 2 plus 2 plus 0. Okay? These two have something in common because 2 of the boxes will have something while 1 box will remain empty. Okay? Here we have 3, here we have 1. This is one of the possibilities, but that 1 is empty is for sure. And then here we have 2 there, another 2 there, but this will be empty. Okay, so these 2 are cases where exactly one of the boxes remain empty. Now the last one, 4, 1 plus 1 plus 2, you see? There won't be any other option. So each one of the boxes is non-empty. And these 3 cases, okay, this is a case where no box is empty or is left empty. Okay, none of the boxes is empty. This may have 1, this has 1, this has 2. It doesn't matter which box. But what I'm seeing or what I'm trying to say is that, when you distribute 4 objects into 3, it's possible that just the box remains empty or 2 boxes remain empty. 3 of them cannot remain empty because that wouldn't be a distribution, okay? Because I have already 4 elements to be distributed among 3. Good. So to generalize this, suppose this is n and this is k, okay? In such a distribution, from 1 to k minus 1 boxes could be empty. It's possible. 1 up to k minus 1 boxes could be empty. So, given n distinct objects to be distributed into k identical boxes, it is possible to have, let's say, j empty boxes where j varies from 0 to k. If j is 0, none of the boxes is empty. So to k minus 1, because all the k boxes cannot be empty. Okay, then what happens? In that case, we are trying to express them in a suitable form so that we can apply some tool which makes life easier for us. Okay? So let's suppose j boxes are empty. Okay? Suppose j boxes are empty. So we can rephrase the problem. We can rephrase then ask the distribution, the number of ways to distribute n distinct objects to k minus j boxes where none of the boxes is left empty. Okay? None of the box is left empty. So now this has a restriction because it requires that none of its boxes remain empty. And this is actually the same thing as saying or counting the number of partitions of a set n into k minus j parts. Okay? And we can count that using the Stirling numbers of kind 2 or second kind. So we are reducing our problem into such a way into some suitable form in such a way that we can apply this Stirling numbers of second kind. First, we require the idea of a partition of a state. Okay, a state is say with cardinality n into k parts is just a family. It's a family of k mutually disjoint, non-empty subsets of S whose union is S. That's what I mean by partition of S into k parts. Okay? Now you see that the sets have to be non-empty. Non-empty and mutually disjoint, and their union is S. Now I'm going to formulate this problem of distributing n distinct objects to k minus j boxes where none of the boxes is left empty in terms of partitions. Because, you see, the number of partitions of a set S with n into k parts is given by the Stirling numbers of the second kind denoted by S and K. Okay, there is an infinite lower triangular matrix or an infinite array, lower triangular array of numbers, of course, which generic term is nk counts the number of partitions of a set S of size n into k parts. Those parts are non-empty. Okay? So this is another way, a different way of counting or saying, rephrasing, saying what we said earlier, stating what we have stated earlier. That is, i.e., S and K counts the number of ways to distribute n distinct objects into k identical boxes where no box is left empty. Okay? No box is left empty. So now we can count those distributions which do not leave a box empty. What about the other ones? What about, we have seen that there are distributions which leave j boxes empty. Okay? How are we going to count them? Well, if j boxes are empty, we've said that it can be considered as a distribution of those n objects into k minus j identical boxes. So we still can count them. Okay? Therefore, see, since we have said earlier that a distribution which leaves j boxes empty could be taken as a distribution of the n objects into k minus j boxes where no boxes left empty. Hence, adding those can give me all the distributions of n distinct objects, k boxes. See? Therefore, the number, then we better find our space. It's very hot in here. Okay. So, the fourth A follows that the number of distributions of distinct objects and k-box identical boxes. Boxes can be given by or is given by, is given by the sum S and J, okay, where J varies from 1 to K. Okay? J varies from 1 to K. Each S and J counts the number of ways and distinct objects could be distributed into J boxes where no box is allowed to be added. And we have this triangle of numbers, a matrix from which we can determine our S and J, or there is also a formula. There are various approaches to the problem actually to determine S and J. It satisfies the recurrence relation with initial conditions. Can be also used. We can solve the distribution problem for any n and k in this way. Okay, by adding, I'll give you just an example. Okay, an example. Example probably what we have already solved in our last lecture. I think we had 41. It was 5 to 3, right? Okay, that example we solved using a different approach. The case where n is 5 and k is 3. Okay, we try to discuss each case and counted the number of possibilities that lead to that case and added the final results to obtain some number. I'm going to obtain that now using this formula. Okay, that is nothing but the sum of S n is 5j, okay, 5j where j varies from 1 to 3, our k is 3. So nothing, this is S51 plus S52 plus S53. Here we have a table. Here we have a table of Stirling numbers of the second kind. See, this is 5. On the 5th row, we have, and the column 2, we have 15, 25, and here we have 1. Actually, there has to be 1 there. So you see, this is 1 plus 15 plus 25. S51 is 1. The number of ways we can partition a set of 5 elements into 1 is just 1, right? So S51 is 1. Here we have 15. Here we have 25. And this is what gives us 41. So, thank you for listening. See you next time.